So it's at the right hand side of this air line. Okay, something here. So you can see here if give the omega, the tangential wave number of surface plasma, it should be larger than the K0 of this air line. So it's need to some special technique to excite surface plasma. One technique just is dipole. I can say dipole is a universal way to excite the guided wave. If a polar person dipole is very near from the air-metal interface, they can excite it because the dipole has a rich Nelson wave special. Okay. Another is just use a prism. Okay. Because prism has total reflection, total internal reflection here. Okay. So they also has some evanescent wave, and this evanescent wave also penetrates this thin metal film and excite the plasma at this air and metal interface. Okay. The thickness of this metal film should be around this skin depth. Okay, it's much smaller than wavelength. Okay, if the thickness is if the thickness of this metal layer is too thick, a wave cannot penetrate into this layer, so it cannot excite the surface plasma, significant surface plasma at this higher metal interface. As I said, because the surface plasma and air dielectric air-metal interface, the tangential wave number or propagation constant should be larger than K0. It is possible achieved by the prism. Okay, yeah, and it's prism layer. Okay, it's prism layer because the K prism sin theta. Okay, maybe this theta here. Okay, prism sin theta can equal to KSP. Okay, this is larger than K0. Okay, this is possible because and the prism, the K is larger than K0. Okay, so it's possible to excite the surface plasma and the air metal interface from a prism metal interface. Okay, because prism interface, the KSP should be larger than the prism because they will decay along vertical prism. So this is the reason why I use plasma this interface. I think the most important one is to use a periodic structure to excite surface plasma. Okay, the K0 sin theta is a momentum provided by the incident wave, the tangential momentum. Okay, in periodic structure they have Fourier mode. Okay, so they have 2 pi p or m here. M equal to 0. It's a positive negative 1, positive negative 2. Okay, they have differential order. Okay, equal to surface plasma. They can excite this surface plasma by periodic structure. So I think the intuitive picture is something here. Okay, something here. You can see that this is effective vector potential of this air. This is a dispersion curve or surface plasma. It's a blue curve. If you have the periodic structure, we can do a periodic expansion. You can see that because it has many different cross points, so they can excite. Okay, mathematically, this is a very simple equation. Okay, this is just periodic structure can excite this surface plasma. I think the most successful example just use the same film with a hole. Okay, same film with a hole, and they can excite the surface plasma because floating. So in last lecture, I think the most difficult part is plasmonic band gap and plasmonic band gap. Okay, I think maybe many of students miss this part, so I'd like to repeat that. It's about the plasmonic band gap and plasmonic band age. Everyone knows for the photonic part, so I just use maybe I use this part. Maybe you can comparatively study. Okay, this is a plasmonic. This is a okay. This is a photonic band gap. For photonic band gap, everyone knows that we give the 1D multilayer structure A, B, A, B, A, B, okay, and repeat them many times. Okay, this is a photonic band gap. Okay, if I assume that emission A equal to emission B, there's no any perturbation, so everyone knows that we know this dispersion curve. just something like this. I get to the periodic expansion at this point. Okay, at this point, this is a standing wave because it has omega equal to ck. This omega equal to minus ck. You learn the photonic crystal. Okay, this is standing wave point. Okay. If I introduce some perturbation, that means Imson A not equal to Imson B due to the couple mode theory, they will split a band gap, okay, and a band edge. Okay. So this is, we call this photonic band gap. Okay. The physical origin of this band gap just constructively and destructively or propagating wave. This is important. It's a propagating wave. Okay. This is a constructively and destructively interference of the propagating wave. Okay. So this is very similar. Maybe there has some difference, okay, between a surface plasma. Okay. Now we'll see the talk about surface plasma. We know that surface plasma also supported in air and a metal interface. Okay. If I use virtual pure boundary condition, I add some virtual pure boundary condition. To this surface plasma, so the dispersion relation with surface plasma will do the periodic expansion. Okay. Okay, it's many. Okay. At this point, it also is called standing wave. But this standing wave is very special. It's plasmonic standing wave. Okay, this is called plasmonic standing wave. This is the two surface plasma along two different directions. You can understand this is one surface plasma propagation from left to right hand side. There's another surface plasma from right to left hand side. When they do interference with each other at this point, they degenerate because standing wave point. Okay. It's a plasmonic standing wave point. Not standing wave. It's plasmonic standing wave point. Okay. This is interference between the surface wave. Okay. Then I introduce the perturbation. So I just cannot.
Yeah, the motion is too large.
Yeah. So I just perturb this boundary, slightly perturb this boundary. Okay, so the diffusion relation becomes something like this. Okay, becomes something like that. So they has gap. This gap we call a plasmonic band gap. This is the plasmonic band gap. This plasmonic band gap, the physical origin of this plasmonic band gap is different from photonic crystal. Because photonic crystal is interference, destructively and conductive interference between the propagating waves. But here, the plasmonic band just interference between the surface wave. Okay, becomes a surface plasma wave. Okay. This is interference. Okay. At this point, we call this plasmonic standing wave. Okay. This is a basic idea about surface plasma, band gap, and band edge. So I go to this figure. Okay. So you can see here, this is the original. It's something like this, right? So here they are splitting two different frequencies due to the modulation. Okay. This is a sine or cosine modulation of this boundary. When they modulation, they are splitting two frequencies due to couple mode theory. Okay, a lower frequency and higher frequency, the difference just between the charge distribution. Okay, a lower frequency, the charge distribution, you can see the field line is something like this. It's quite similar to the field line of the traditional. You can see this is the traditional flat surface. You can see this is the charge density, positive, negative. This is the ideal flat case. But when you modulate the lower frequency, you can see it's similar. is similar Z. So the perturbation is small, so it's at a lower frequency. But at a higher frequency, the positive and negative, you can see the distribution is different to this. You can see the field line, okay, was distorted. Okay, it's all distorted, and charge distribution was different. Okay, this is called plasmonic band gap. Okay, I also do something about this. Okay, this is for the square grating. Okay, it's square grating. You can see at a lower frequency, the E field is concentrated in the top region, and high frequency, they are concentrated in the top region. Okay, this is very similar to the photonic crystal. Everyone knows that according to the verification principle, at a lower frequency, the EM energy will focus on the dielectric band, and a higher frequency will focus on the air band. But here, similarly, it focus on the top region and top region, so they have some splitting. Okay. But in this structure, the band gap, is not a real band gap. It cannot open up. So, but here you can also see that it has the same color space. The field is weak. You can see it's distracted interference. It's weaker. Okay, it's distracted interference. This is contracted interference. So field is strong. So people can use this band edge for the lasing. Okay, to plasmonic band edge laser because the E field is strong. Okay, so how to open up a band gap? Okay, in literature, how to open up a band gap larger, to open up a large plasmonic band gap. What's the way? It's very similar to a photonic band gap. The idea is here. Okay, this is a grating. Not go purely structure. This is grating. Okay. How to do that? I just draw it. You might smile. Okay. Okay. This is metal. They use two dual phase. Okay. Dual interface. Okay. Gratings. Why? Why is this structure? Remember diamond structure. Remember diamond structure in 3D photonic crystal. They have offset, right? They have offset. This is very important. So I turn back. If I this photonic crystal. So everything are same. So people just use same ideas. I just go to the wood pile. Okay, you can see this is wood pile. For wood pile, this is vertically. This is horizontal. This is follow each other. Another thing has offset differently. You can see that. Okay, so I said when you stack something with offset, it has opened up a band gap like graphene or something like this. So this is very similar idea. It has introduced some offset. Okay, you can see it's not aligned, it's an offset. They have two interfaces and they can interference with each other to open up a plasmonic band gap. In this structure, the plasmonic band gap and the band edge become very significant, so people can do some lasing. Okay.
Sorry, could you go back to the previous slide? Hey, Sha Wei.
What's this?
No, just your handwriting.
Oh. Okay.
Go back a little bit. Up a little bit. Yeah, in the figure you see that you make perturbation, and then you open up the band gap.
Yes.
Right. So here you introduce another side, another grating.
Yeah.
So the question is, you already open up the band gap.
Very small.
Yeah,
very
this
small.
This is further.
Yeah, this is large.
Okay.
It's large.
That's one thing. Another thing is that you in the picture the omega K, this diagram show people where is the band edge, where is the band gap.
Okay. This is a simple. But in photonic crystal is not so simple. This is how photonic crystal is the band edge.
Yeah,
so group velocity equals 0 is band gap. But here this is all can see this is band edge, this is band gap, similar. But if group velocity not equal to 0 due to lossy property. Okay, it's lossy. So you cannot see this is not omega K, it has omega real K, the omega embedded K. They have two kind of complex band diagram. They become very complicated because the metal is lossy. So this group velocity typically at here is not so flat.
The point is that the band gap is talking about the difference.
Okay, you can
between
see not
band edge,
so,
right? Band gap is the difference between two. The region
yeah.
between two band edge.
Yeah, this region. But this region typically is small. Okay,
so how can you have a band gap? You can see in the picture. You see the band gap. You stay in the graph. You have mid frequency.
Yeah, middle frequency. So, this is also middle frequency between lower and higher.
So it means that in the band there's some modes that can be supported in band gap?
No, it's no electromagnetic mode. It's electromagnetic mode is weaker. It's in photonic band gap is zero density state. No electromagnetic mode.
So what's the picture tell people?
But here you can see from here this is a weaker field. It's constructive interference. Okay, like a photonic band gap, no EM field. Okay.
So for the band gap, there's no constructive interference there?
No constructive. This is destructive interference. This constructive interference in band A is destructive interference in band gap. Okay. It's everything is similar to the photonic crystal, but the thing is that this is the interference by the surface wave. This is one thing. Another thing is lossy material, so the dispersion relation become very complicated because it is lossy material. Okay. But this phenomenon, from my understanding, this phenomenon cannot understand quite well until now. People study very recently also published paper in physical review. B uses band A to do a leading to understand it, how to open up with band gap, how to draw its dispersion curve. This is wrong dispersion curve because I said it has real part of K and imaginary part of K. It should be two part, okay, because the lossy media is complex. Okay. So this is the difficult thing. Okay. The first method to excite surface plasma is this is use the subscatter. Okay, this is also learned in the last lecture. I just move faster. This use some subscatter. The subscatter produce evanescent wave at the tip, this very small region, and it excite the surface plasma. So this is easy to understand. So this subscatter similar to Hertzian dipole. It's similar to Hertzian dipole, so they can excite the surface plasma. Okay, so in last lecture we talked about this.
Do we need very large energy in order to make the scattering exist that couple the surface wave and the plasmatic wave?
No.
No requirement for that?
Not necessary requirement for that. This is visible light is okay.
I mean the energy. I mean the intensity, not the photon energy.
No. What's energy?
The power, for example.
Not necessary. Not necessary. It's not laser. Not leading. It's not necessary very large power to do that.
To excite it.
Right. Not necessary to do that. But you can see if very little power, a surface plasma to the propagation, very little distance, you cannot find that. Okay.
Yeah.
A distance you should be. If you want to be propagation long distance, you must give a high power. Okay. This is the key issue. Okay. If you see the propagation, okay, they should get a larger power. Okay. So I move to this. The multi-layer plasmonic system. In last lecture, I also talked about this. I also think it's important. The multi-layer plasmonic system, this is metal, it's air, okay. If the metal thickness is around the skin depth, okay, around the skin depth, so the surface plasma at two interface can interact with each other. Okay. If very thick, the wave will decay very fast. It does not interact. But it's a thin layer. It can interference. When there interference, according to couple mode theory, they are split two eigenmode. Right. First only have one eigenmode. Now has two eigenmode. Okay. This eigenmode has a very interesting feature we call long range and short range. That I made to draw this picture. So it has two band diagrams, Re, beta, omega. This is real part of this propagation constant. Okay, this is original. This is the original one. Okay, I change the color here. This another. It's split into two. Okay, this line we call this odd mode. This red we call this even mode. The even mode is something I draw this picture, something like this. You can see the symmetry, called symmetry mode. The odd mode, something like this. Okay. This even mode and odd mode to support this structure. Okay. This is I just draw this. Here. This when you derive, you can see this. Okay, it's even mode and this odd mode. Okay, red is even mode, and green is odd mode. This is real part of the beta. Okay. So how to excite this two mode? It just change the, change the angle, change its freedom. Maybe this is a metal layer. Okay, this is metal. We'll change a different angle. It's okay. Okay. Maybe theta 1, they can excite all the mode. The theta 2, they can excite another mode. Because they have different key. Okay, I just use another color. But I'm going to use plane setting. You can see you give a same omega. The two mode have different key, right? So if you want to excite it's a pure odd mode or even mode, you just change the angle of the prism. They can provide different tangential key, right? Different tangential key we can excite due to momentum image. This is way to excite them. Let's go back to flag. So this is the way. But I think the most interesting thing is the imagery part. It's the imagery part. So that's a complex dispersion curve. It's the imagery part, beta, omega. You can see for the imagery part, it has a, let me draw this picture. It's also similar to that. Something like this. I use different color. This should be even, should be larger. Even. Okay. Even should be larger. This blue. This is larger. This was small. You can see, if I give a, this is even, this is odd. This is a picture. I just go to this better picture. You can see, even mode, the odd mode in here, the loss is smaller. You can see, you give omega, this is smaller imaginary part of beta. So the loss is smaller. This imaginary part is the real part. So plasmonic is a difficult thing that you have to draw two kind of dispersion diagram. One is the real part, one is the imaginary part. This is because this is a lossy material, dispersing material, so it's become very complicated. You can see the loss is smaller, so they have propagation on a long distance. Okay, because you can see given omega, okay, the imaginary part of beta is smaller, the real part is higher. Okay, so they can propagation long distance. We call long range surface plasma. Okay, another thing, when you decrease your thickness, the even mode will increase the imaginary part of omega. You can see, from 60 to 50, they will decrease. Okay, it will increase the imaginary part of omega, but this other mode will decrease. That means when you shrink the thickness of the metal layer, the symmetric mode will confine in this layer. Okay, strongly. When you shrink, they will confine. So this symmetric mode cannot propagation so long. But when you shrink this layer, this asymmetric mode does not confine this metal layer, but they confine this dielectric layer. So this is called a long range surface plasma. So this is quite different nature. Okay. You can see this calculation because it's not so clear. Maybe red color is better, green kind of thicker. You can see your lecture notes.
So it means that this odd and even modes exist whenever you have a structure with very thin metal, right? If it is not that structure, you don't have this odd and even mode.
It should be very thin. They can split it.
Yeah, that's the case that you can talk about. And yet you have the imaginary part, right?
Right.
So this imaginary part of beta actually telling that it will loss. I mean,
yes.
During the propagation.
Yes.
So means that, look, you say that one of them is long propagation, one of them is short propagation, but all of them have loss.
Yes.
So when you say long, it's not very long.
Not very long, but it's compared to, when you shrink, they become longer and longer. This part, when you shrink, this become lossy will reduce. Okay. So this is the nature.
In both cases, in the forward, in the backward.
You can see, while this has different trend, while decrease the thickness for this even mode, they increase the loss. But for all the mode, they decrease. You can see
The two lines is the same.
Right, but no, it's not the same, but it's a green color.
Which one is which?
Right.
Which one is which? 50.
This is the same. This is the same.
Oh.
Okay. It's reverse. Okay. So this is very interesting nature. Okay. You can see the lecture notes. It's not clear. So this is nature. We call it even more. They can be used. They can solve this curve. I solved by myself with the final difference method. 1D final difference method. It's easy to solve. Okay. I solve with finals. Okay. So this is something I talked about in last lecture. In last lecture, I also talked about the local plasma. A local plasma. Okay. In local plasma. Okay. I also talked about in lecture. This is for nanoparticle. Okay, for nanoparticle. This I do this local plasma nanoparticle. You can see here. This is a very classical picture. It has a bulk electron within the nanoparticle. It's mainly bulk electron. When you add an E field, the bulk electron will oscillate up and down. Okay. So the important thing, the size. Okay. If the size of a nanoparticle is comparable to skin depth, the electromagnetic wave can penetrate all the sphere. Okay. Like a micro, for microwave, okay, the thickness of this layer typically is some millimeters. Millimeters is much larger than the skin depth for this circuit plasma. It cannot penetrate. Okay. But for nanoscale, the distance typically only smaller than 100 nanometer. So EM wave can penetrate all the sphere. Okay. Grasp all the conduction-free electron. They grasp. Then it oscillates all the electron up and down. Okay. This is called a plasmonic effect, so local plasma. Okay. This is a very interesting phenomenon. Okay. They can penetrate. But this scattering for this scattering for its sphere, they have two kind of laws. One called absorption loss because of metal, another called the decay loss because they have some scattering. They have some scattering. So they have two kind of loss. Okay. This is a polarization charge distribution. It's similar to a dipole, Hertzian dipole. Go
But that is far field, right?
No. This is a near field.
You see the distribution of field look like a far field.
This is This is a field line. Positive.
Okay, field line.
Field line. It's not far. Because I talked about this in last lecture, but a few students attend my lecture, so I have to repeat it with them. Another is just resonance condition. Resonance condition is difference. Okay, it's just resonance condition is difference. I have no time to talk about this, but I talk about a more important one. Okay, the physics about scattering for sphere. Okay, if a sphere is very, very small, okay, so much smaller than wavelengths, we call it Rayleigh scattering. The far field pattern, far field scattering pattern is similar to a dipole. Okay, similar to a dipole. They call Rayleigh scattering. They can explain why the sky is blue. Why the sky is blue? Because the particles scatter EM wave. The particle scatter blue light is much stronger than the red light. So it's a red light is blue. Another will increase the size of a nanoparticle. Okay, they have the mid scattering. You can see the forward scattering. Okay, forward scattering larger than the backward scattering. Even you increase the size of particle further, it has much stronger forward scattering. They call it mid scattering. Okay, this is they can also explain why the cloud is white because it's scattering all the different color are almost same, depending on the size of this scatter. So this is scattering pattern for sphere. I also talk about this many things before. Okay, for near field and far field for the a nanoparticle or Hertzian dipole. Because a small nanoparticle is behaving like a Hertzian dipole, you can see here in the near field they are polarized. You can see the E field. This is the E field. E field is polarized along this direction, so E field is very strong here. But at the far field, you can see the E field is concentrated along the K direction, the far field. Another thing is the intensity. Okay, because I enlarge the intensity 10,000 times to make this color seamless. The color of sand. This is the basic physics. Okay, I talk about this maybe in basic Maxwell equation. Okay. This is in last.
Any size, particle size difference between the Rayleigh and the mid scatter, the particle size. For the mid and the Rayleigh.
Mid and the Rayleigh, typically for Rayleigh scattering is much smaller than half wavelengths. It's very small. Okay. Mid scattering is comparable to wavelengths. It's maybe in plasmonic sphere, I said the particle size should be much smaller. It should be comparable to skin depth because it can penetrate. So at this situation, It's really scary. Only have dipole mode. Only have dipole mode. Okay, only have dipole mode. Even for 100 nanometer, only have dipole mode. Okay, dipole mode will dominate.
But some people claim they still have plasma, but the particle size is much bigger than the skin depth. So would that be true or?
This is good. They typically call it high order plasmonic mode. Okay,
so it's still plasmonic, but higher.
Right. But typically we talk about low order plasmonic mode. Okay. So the regular way is use mean scattering, mean theory to analyze the sphere scattering. Okay, this is called mean scattering. I use mean scattering to analysis. Okay. So I give the definition of absorption, scattering, and extinction cross-section in last lecture. How about the scattering cross-section? Scattering cross-section is the total scattering power of nanoparticle as a function of the frequency. Okay. You can see that it's real part 1 or 2, E scatter field cross H conjugate scatter field. Okay, dot ds. This part is a scatter power. Okay, scatter power over the incident energy flux. So this is dimension is area. Okay, they call it scattering cross section. Scattering cross section is a way to see the scattering power of nanostructure. It's different from scattering pattern. Scattering pattern is angular spectral distribution. Okay, when you do the average of all the spectral together, you call scattering is scattering cross section. Okay, it's just one value for one frequency, the total scattering power. Another
difference if you use Rayleigh instead of me to do the simulation.
Right, well, I think in any situation we should use means.
Not use Rayleigh.
Right, it's very dangerous. Okay.
Why dangerous?
Well, because for Rayleigh, typically the people use electrostatic approximation. We see that everything are Laplacian equation, but it's very dangerous. Use that. Typically, especially sphere is small, but there are many spheres. They have retardation.
So if the size is very small, you still can use mean scattering.
Right. Mean scattering.
Not necessary to use Rayleigh.
Right. Not necessary to use Rayleigh. Mean scattering is more rigorous theory for sphere. Okay, even if very small. Okay. This absorption cross-section just absorb the power. Okay. You can say this is a Poynting theorem. 1 or 2 real part equals H dot and dot ds. This is absorption power equal to sigma E squared. And all the incident power. This is absorption power. Extinction cross-section just absorption plus scattering, hold them together. Okay. This is I also talked about this in last lecture. So this part I like to move slower. Okay, I just go down this part. Okay. Because in last lecture I had to finish absorption, scattering, extinction, cross-section. So absorption cross-section is just absorb the total absorbed power of this particle. Scattering cross-section just total scattering power. You can understand total scattering power, all the direction, add them together. Okay, for the particle. And extinction cross-section just absorption plus scattering. This is intrinsic loss, including absorption loss and leakage loss or radiation loss. We put them together. This is 3. Okay. This is a very significant picture. I think everyone should understand this picture. Okay. You can see for gold with a radius 50 nanometer, you can see the absorption cross-section. You can see the extinction cross-section is dominated by the absorption cross-section. I mean, scattering cross-section is smaller than absorption, so the particle has they can absorb EM energy, okay, then scatter EM energy. So the absorption capability is larger than the scattering capability. For very small, it's a metallic nanoparticle. Okay, so if you use nanoparticle to heat up, some skins, okay, you can use this small nanoparticle because it absorbs EM energy. Okay, this is a silver. This is a gold. Okay. Another thing you can see, this is a normalized cross-section. I calculated this scattering cross-section and over this pi a squared. This is a geometrical cross-section. You can see almost all of is larger than 1. You can see. They mean that this cross-section is larger than the geometrical cross-section in this nanoparticle. If you increase the radius change, you can see the scattering. The scattering is larger, it's larger than its absorption cross-section. Okay, you can see here. For a larger nanoparticle. So increase the size of nanoparticle, increase the scattering ability of nanoparticle. Okay. So this is an important thing. You have to choose the particle size of particle. Okay.
Then maybe multi-mode and so-called high.
No multi-mode. Only
it's only single. All of them still single mode.
Right. I'll tell you why it only has single mode later. No problem. Okay. This is single mode. No net particle. Another thing, we compare the metallic sphere, left figure, and the dielectric sphere. This is multi-mode. Okay. Dielectric sphere. Everyone has a 100 nanometer. This is gold. This is with n equal about 3.5 refract index, similar to silicon, you can understand. But here I use a lossless kit. You can see here, this is a very interesting figure. Okay. You can see here, I decompose the total extinction cross section with the TM part and TE part. For sphere, it also has TM part and TE part. Okay. Let me explain this. For sphere, okay, if the E field along the R direction, okay, the edge field is tangential. This is edge field. This mode we call TM mode. Okay, you can see TM mode can excite the plasma. Why? It has surface charge because n dot d is not equal to 0. Okay, another is called TE mode. Edge is along the R direction, and the E field is tangential. That means E has the E theta and the E phi. Okay, this is H theta and H phi. Okay, this is called TE and TM mode. You can say TE mode cannot excite the surface plasma, right? It's TE mode because n dot d equal to 0. Okay, no surface charge. No surface charge because E is tangential to its surface. It only has E theta and E phi. This is basic concept. This is physical reading. Then I go back. This is my calculation with me series. You can see I decompose the total extinction cross section with the TM part and TE part. For this metallic sphere, you can see TE part contribution is very small. Everything has TM, only has one mode. Even has 100 nanometer. Okay. They have high order mode, maybe 100 nanometer. Yeah. So it's usually very large sphere. So I think plasmonic effect, only one mode. It's dipole. This mode is dipole mode. Okay, just dipole mode. Just I show this picture. This work is done by my colleague He Shiquan. Okay, they draw this dipole mode. Okay, this nanoparticle, this near field distribution. Okay, this diameter 50 nanometer. You can see this E field is polarized along its direction. So it's very nice dipole mode. So I said even 100 nanometer gold has dipole mode. And this dipole mode is by a TM wave. I said TM wave, the E field is along R direction. They produce a surface charge because n dot d is not equal to 0. But TE mode, n dot d equal to 0 and no surface charge. We cannot excite surface plasma mode, cannot complicate this. Okay, this is. But you can see this dielectric. Okay, this is a whisper gallium. Dielectric is quite interesting thing that you can see. At this window light regime, it has many modes. So first, fundamental mode is TE mode. TE1, you can see is TE1 because I decompose the total with TM and TE. This is TE domain. This is TM domain. This is TE domain. This is TM domain. So TE mode, TM mode, TE mode, and TM mode from lower and higher. This mode is called whisper gallium mode in dielectric. Another thing, you can see that the first fundamental mode for plasmonic is TM mode. Because I said it has surface charge, it has plasmonic resonance. Right? But why this first fundamental mode is TE mode for dielectric? So this is an interesting thing. So you can see this resonance condition. This is resonance condition. It's approximate. Okay, this is resonance condition. Okay, you can see this is electrostatic approximation. That has physical meaning. One epsilon is metal plus 2 epsilon m is dielectric almost equal to 0 and the resonance. Right? This is resonance condition. If metal the epsilon is negative, very important, they can cancel the 2 epsilon by dielectric, produce a plasmonic resonance for sphere. But for dielectric, they cannot. No has pole. No has this pole in here. Okay, no pole in here. So similarly, rigorously for me scattering. For me scattering, they also have two kinds of pole. One pole is for the TM mode. They give the first lowest order, or when n equal to 1, the solution with this order gives the plasmonic resonance. This is the T mode. This is what called TE mode. Okay. So when your frequency around this resonance frequency, it has a higher peak. Okay. For surface plasma, they can certify this. Okay. But for metal, okay, they can realize just emission 1 plus 2 emission 2, they can be around 0. But for the dielectric, they cannot because add them together, they add them 0. Okay. Okay. This is the reason. So you can see mathematically the scattering cross section. You can see this is a reflection coefficient, T and Tm, add them together. When this has a pole, they go to infinity, right? They're very large. They have a pole. So you see many peak, just a reflection coefficient, over this pole. Okay. The T wave and Tm wave, T wave and Tm wave. You can see that distance is larger, it becomes smaller. Okay. Because high frequency, the resonant peak become very dense. This is high order whisper gallium mode become very dense. Okay. Well, this is lower. So this is a very rich physics in here. Okay, this is quite different thing. Okay. For dielectric and metal, for TE and TM. Another, you can see, I also draw an interesting picture for 50 nanometer, smaller sphere. The extinction cross section metal is larger than dielectric. Okay, invisible light regime is larger. That means dielectric is not small. Maybe it's larger at the ultraviolet. But in invisible light regime, metal should be larger than the dielectric. So this is the reason why we can plasmonic can do the small. When the dielectric sphere become very small, its scattering power become very low. But the plasmonic become very small, situation is quite different. It still has a very strong scattering ability or absorption ability. This is our advantage. So this is the reason why plasmonic can do the very small. Okay, it still can be large. This is
But this is extinction, not the scattering.
Right, no problem. Let me to show another figure. Okay, about co-shell structure. Okay. This is just one simple case. Okay. Okay. I know someone to work on the whisper gallery mode, right? To work on whisper gallery mode. Okay. I hope you can understand this why they have a peak, because it has a pole reflection coefficient. Okay. Okay. This is whisper gallery mode. Whisper gallery mode condition I just mentioned because some students work on whisper gallery mode. Okay. Whisper gallery mode condition for TM wave, for T wave, just this two. Okay. You can solve this. But every resonance frequency are complex. Even lossless media. Even lossless media, every solution is complex. Why? Because it has a leaky loss, radiation loss. So it's complex. So why do the real frequency? Because we only have a real frequency. When we real frequency is very close with the complex frequency, they have the resonance. Okay, they have the resonance. This is a basic idea. Some your students called Zhang Yiyuan, right? They asked me to solve this kind of problem. I saw him find this whisper gallery. Okay. It's a whisper gallery. Okay. So I have two slides for plasmonic coupling. Okay. Before I talk about plasmonic coupling, you can see this is shape dependent. I check the particle shape. You can see the plasmonic resonance peak can be significant change. This is a feature. You ask me how to predict this peak, you simulate, no choice. Simulate in the full wave simulation software console, FDTD, Lumino, or maybe CST. Okay, this three is better because it's too complicated. I cannot predict. Another work is done by Sha Wei and me. Okay, as supervised by Professor Wallace Chai. Okay. At that time,
from you.
Yes, right. This is not by me. This is theoretical result. But at that time, I remember you asked some professor from UST. They have fabricated this nano prism.
Oh, this is what done by us.
You fabricate by yourself?
Here.
Okay. They have some prism. When they fabricate the prism, they put that prism in the solar cell. They find some peaks. Okay, find some enhancement. So the Dante led me to help to.
No, this is ours. All things are from our work. In Hong Kong, you.
Yeah, I know.
The results are from Hong Kong,
okay.
Experimentally.
Okay, I know it's experimentally. So I asked me to calculate this curve to predict to explain the physical reason Oh, it's many peaks. Okay. So that I just explain that this is water. It's a freedom. It's a freedom in water. You can see that when you change the polarization field from, you can see from polarization to vertical, you can see from the, this is a fundamental peak. Okay, you can see the peak are splitting, the different. This is the dipole mode. You can see this dipole mode. Okay, along it's horizontal polarized. In vertical polarized, also has dipole mode, but a little bit different. Okay, so they have splitting. You can see the different polarization have different mode. Another, it also has some high order mode. You can see this lower shorter frequency. They also has a small peak. Not so strong. You can see high order mode typically is weaker. Okay, not so strong. You can see it's not dipole mode. It has something similar to quadrupole or something. You can see this is okay. This is a polarization dependent. It's a polarization dependent. Okay, for surface class, different polarization inside a different mode. Okay, for sphere, I think it's the same because it's symmetric. Right? For triangle, it's not symmetric. So this one is different. Okay. It's not symmetric. This is the reason. Has different mode. Okay. Another is a very standard structure, very famous is sphere chain structure. Okay. This is experimental result. This is simulation. A bottom simulation. You can see agree very well. You can see if a sphere are well separated, okay, they're not coupled. I mean the distance are not coupled. Typically, the distance equal to 1 diameter. If this distance d, we call this d. This d is larger than the diameter. We can see the two nanoparticles are not coupled. This is a rule. Okay, typically rule. Okay. When the distance is larger than the diameter, the coupling can be ignored. Okay. This is well separated. This is a close packed. Okay, close pack. You can see the well separated, they have scattering field, they have interference with each other, right? They have interference pattern. Interference pattern. In all the space, they have scattering pattern, interference with each other. But very close to each other, you can see they couple very strong. They become a guided wave, similar to guided wave. Okay. They can guide along this particle. Okay, this particle. So they couple each other. So this is quite different. This is a very famous picture. What's the physical reason why which kind of mode exists? Okay. Typically exists two kind of mode. One is called longitudinal mode, another called the transverse mode. For longitudinal mode, when E field is polarized along this direction, E field is polarized along this direction. It has a positive, negative polarization charge. You can see it polarized along this direction. Okay. It has polarization charge. Okay. You can see the different at this part that is attractive. I mean the positive, negative, the electron from here can be attracted to here. So oscillation distance become longer. Okay. I mean the first sphere, the electron can be only oscillation within this nanoparticle. But when they couple, the E field, it has a polarization charge. They have a Coulombic force. The Coulombic force is absorptive force, attractive force. The attractive force makes the electron oscillation in larger area. Okay. So the resonance frequency will redshift. I mean they shift for long wavelengths. Okay, because the resonance length is changed. Okay. So the one sphere I similar to I just is intuitively. Maybe this is oscillation. Okay, distance. Okay, oscillation from here. If they couple, maybe the oscillation become larger. This lambda oscillation. Okay. Because it's Coulombic force, you can see the Coulombic force is attractive force. Okay. The electron, if electron is an attractive force, so you can do here. Okay. So this is another. If E field is polarized along vertically, you can see they are repulsive, right? They're repulsive force. They're same. They're repulsive force. So they oscillatory at a shorter distance, right? So they had a blue shift, okay, shift for short wavelength. This is just due the Coulombic force. It's repulsive, it's attractive to make this resonance length change. Okay. So this is a very standard longitudinal mode and transverse mode. I use this in solar cell. I think it's successful. It's successful. Another thing, this last page is a co-shell structure. Okay. The co-shell structure. You can see it's a co-shell. This may be air, and maybe dielectric, this is metal, this is cold shell, a very famous structure, cold shell structure. Okay. In cold shell structure, how to understand the splitting eigenmode? For the sphere, okay, this metal, this Joule model is very coarse model, has a physical meaning, plus 2, but this air, I just equal to 1, is equal to 0, so this is resonance frequency, omega p equal to square of 3. Okay. Another, this is a cavity. I think outside the cavity is metal, inside is air. So I just change the rule. You can see this is 2 metal plus 1 dielectric equals to 0. So this is different resonance frequency. Okay. So I means initially this is metal, this is air. We know image of metal plus 2 image of air equal to 0. This is resonance condition. Okay. So this is a first figure. 2 equal to 1 is air. This is a metal, right? This is vertical. Then I change. You can see it's 2 metal plus 1 because this air become a metal. This is a metal and become air. This is a complementary structure. This is a complementary structure. So I change the resonance condition. Okay. So I get this omega equal to square 2 over 3 omega p. Okay. When they become a cold shell structure, they have 2 kinds of mode. One is lower. You can see this is dipole mode. This is a positive, negative, and negative. You can see this is dipole. Okay. A high order mode, you can see they change the sign. This is high order mode, so it's lower frequency and higher frequency. Okay. Lower frequency and higher frequency. This is an intuitive picture to understand. This is a dipole mode. Typically, use plane wave only can inside this lower mode. It's very difficult to inside the high order mode. Except you use some evidence wave or use dipole to inside that. Okay. So this is an interesting picture. Okay. I draw using me series. Okay. I have a code to do a cold shell structure. So where it's not difficult. Okay. Just few hundred lines. Okay. You can see that for single sphere, here is blue line, and a cold shell. I use a code is 30 nanometer. Air is 30 nanometer radius. Shell is 20 nanometer. Okay. So total size is similar to single sphere. Okay. Then I use a core is 40 nanometer and a shell is 10 nanometer. I mean I shrink the thickness of a shell. If I shrink the thickness of a shell, the surface plasma at least 2 sides of the shell will interference. It's 6, right? Well, I mean this is shell, right? If I do this very thin shell, it's very thin. This surface plasma at these 2 sides will strongly interference each other. Because I said, because it's small compared to skin depth. Okay, so this can interfere with each other. When they interfere with each other, you can see the value. Okay, this is a extinction cross section, very high. Okay, so use this structure, they can do a super scatter or super absorber. Okay, this maybe the concept provides a 泛闪回。Use this super scatter. Okay. They can do this kind of thing. You can control this. But I think it's not easy to fabricate. Okay, it's not so easy. But people now can fabricate maybe 3 layer, 4 layer. I know some group can do 3 layer. They can do this cold shell structure. Okay, so you can control that. So I think the fundamental thing is that the surface interference. Okay, because plasma decay determines thickness. If the thickness is thin enough, and in top interface and bottom interface, they can interference. Okay, like in the out surface of a shell and inner surface of a shell with interference. This is a very unique feature. Okay, like when you perturb this boundary, purely boundary, the surface plasma also can interference. It's a surface wave interference or evanescent wave coupling. This is quite different from the photonic part. Okay, so this is a unique nature of this surface plasma. Because I think you miss the course. You know, in last course, I finished here. Okay, so today I just moved to 4K. In last course, I finished 12. You can learn the video by yourself. Or else you just miss the local plasma resonance. Okay, you only learn the surface plasma resonance. I think local plasma resonance is also important. Okay, plasma only has 2 parts: surface and local. Okay. So this is okay. So any question about this lecture?
Sha Wei, I found a lot of theories here actually extremely close to the more theory in EM field, in the sky field.
Yeah.
And the problem is how are they being used?
Yeah.
They
you can see this is from
scale.
yeah. This is just Professor Chu's book. Everything are same. But the difference thing is just how to define the key, because the imson become negative. When the imson become negative, everything are different. The mode.
Yeah, then how can they be used experimentally?
What's the meaning?
Can these properties be used in experiments?
Why you know people just do the field enhancement, do a search or do some kind of application, or maybe do a super absorber. They can kill some cancer cell with this method, so they design some nanoparticle with a strong absorption or scattering of capability.
And how successful are those trials?
Oh, this one can be commercialized. It can be commercialized.
Seriously, it's another thing because it's talking about the exciting mode and
they can enhance
each other. It's actually nonlinear effect. You cannot use the source as the example directly because it's far too complicated in that way.
The source is another thing called biosensing. They can shift.
Biosensing, yes,
biosensing is commercialized. Right. For the deep reflection, it shapes the deep reflection.
Is that what Alexander asked? I guess are you asking? Did he answer the question?
In application.